Good morning, AP Statistics. Here we go again. Another snow day. Good for you, I guess, but we still have some things to do since this is day number 9. Your tests are graded. You will definitely get those back when next we see each other. Results were all over the board, anywhere from not very good to really, really good. Everybody fell somewhere in there. We are going to move on, and we're going to move on again to inference, which we've talked about all last chapter. Remember, inference means to make an educated guess about something without having all of the information. And we give some examples. If we were sitting in class here together and you heard some glass break out in the hall and somebody scream almost at the same time, you might infer that they're screaming because they dropped something and broke it. And you might be right. But it's also possible that they dropped something and they saw a ghost at the same time, and that's why they screamed. Not likely, but you get the idea. You're making an educated guess about something without having all of the information. Now, we are making educated guesses about populations. We're going to start doing something called forming confidence intervals. And the most familiar example to you, I would imagine, would probably be presidential approval ratings. I just looked up on the internet. The current presidential approval rating is about 38%. At least that's what they think it is. But then there's always this little plus or minus thing at the end. And the one I looked up happened to be plus or minus 5%. And the thing we need to spend a lot of time talking about is, what does that plus or minus 5% mean? Now, we do know that if you go from 38 down 5%, you end up here, and 38 plus 5% ends up there. But the question is the real approval rating somewhere between 33 and 43? Is it there for sure? Do we think it's there? Is it probably in there? Would we like it to be in there? Those are the kinds of questions that we need to ask. And it turns out the answer is no. You cannot guarantee me that the real presidential approval rating is somewhere in there. That's not true. It turns out you can't even say, well, it's probably in there. Because the problem is, it either is for sure yes in there, or it's not. Whether we know the true answer is kind of irrelevant. I've given you examples similar to this before. Before you flip a coin, the chances that it's going to land heads or tails is 50-50, okay? So before I do this, now that I flipped the coin, I can't even really ask the chances, hey, what are the chances that it's heads? It already occurred. Just because I don't know the answer, it's still not a legitimate question to even say, hey, what are the chances it's heads? It's a little bit like asking, I don't know how many of us believe in God, hey, what are the chances that God exists? That's not a legitimate question. He either does or he doesn't. Just because you don't know the answer doesn't mean you can ask the chances of it. It's already a done deal. On my way into school this morning, I was in here before school got canceled already. I had a pretty good feeling that it was going to be canceled, but I could not even ask when I was driving in, hey, what are the chances that school has been canceled? Mr. Javitsky's already made that decision. It's either yes or no thing. Just because I didn't know the answer yet does not allow me to ask what are the chances of it. Now, I can ask, hey, what are the chances school will be canceled tomorrow? Because it hasn't happened yet. So we're going to spend a lot more time talking about what does it mean? Is the real answer in there? Is it probably in there? Do I think it's in there? Let's save that for a little bit later. Let's go to something, again, familiar to you. So let's look at U.S. teen texting. And let's just say we know that the average number of texts sent per day is 90. I don't know how that fits with you, but we'll pretend. I looked up on the internet. I saw answers anywhere between 60-something and 120-something, so I kind of took an average of those. And let's just say the standard deviation of the population is 40 texts per day. I would probably think that the population of texts percent per day by teens is not normally distributed. I don't know that, but I've got to imagine a lot of you are in here, and there's probably some super texters that's all they do, and they kind of skew the results a little bit. So anyway, this is what the population looks like. If we wanted to ask, hey, what's the mean number of texts sent per day, we could take samples the size 100, and we would be forming the sampling distribution. Now we know that the sampling distribution and the population have exactly the same mean, right? It's an unbiased estimator. We also know that if we take a sample that big, that even though the population is not normally distributed, the sampling distribution will definitely still be normally distributed, and that's via the central limit theorem. We also know that we can use this formula for the standard deviation of the sampling distribution because Well, 100, is that less than 10% of the number of U.S. teams out there? Well, I would dare say that there's more than 1,000 U.S. teams. So because we took a small sample, we can legitimately use this formula for the standard deviation of the sampling distribution. So the population looks like this, but the sampling distribution looks like this. And here's what we'd like to notice. If this is the standard deviation of the sampling distribution, then if I go one standard deviation this way and one standard deviation this way, that puts me between 86 and 94. Now we already know from beginning earlier the year that 68% of the numbers are going to be within one standard deviation of the mean. What that means to us is if we go out and take bunches and bunches of samples, 68% of our samples will come back with a mean between 86 and 94. That is, 68% of our sample means will be within one standard deviation of the true answer. And if we keep going, we know that 95%, right, 68, 95, 99.7 rule, we know that 95% of our sample means will come back between 82 and 98. And that's not all that far away from 90. Now that's mostly a reflection of the fact that we took such large samples, and good for us. But the point is, 95% of our sample means will come back within 2 standard deviations of the real mean. Let me say that again. 95% of our sample means will come back within 2 standard deviations of the real mean. The problem is we really want to take that statement and turn it around. I don't really want to know how far from the real mean my sample mean is. I want to know, hey, how far from my sample mean is the real mean? Because my sample mean is the only thing I actually know for sure. In real life, we don't know the real answer, right? We go out and take a sample. So here's what's going to happen. Let's take a sample mean, pretend we get a sample mean right there, okay? If I then extend my sample at either side of this, 2 standard deviations like I have up here, which would be a distance of 8, if I do that, I move 8 either side, I can form what's called a confidence interval, just like they did over here. What I'd like you to notice is that my confidence interval, which extends from here to here, hey, that actually does contain the true mean. And I can get another one. Suppose I get another sample mean down here, and I extend 2 standard deviations either side, and I form a confidence interval just like this. Hey, look at that confidence interval contains the true mean as well. Now there are some bad samples. If I get a sample mean out here somewhere, and I extend 2 standard deviations either side of that, look at, now I formed a confidence interval, but the true mean is not inside that. This would be a bad confidence interval. I don't want this, but it does happen sometimes. What I'd like you to notice is this. How often, if you get a sample mean and then extend and make a confidence interval that extends 2 standard deviations either side, how often is your confidence interval going to contain the true mean? Here's some examples where it does. Here's an example where it doesn't. What I'd like you to think about is this. If my sample mean, as long as my sample mean is within 2 standard deviations of the real mean, if I then extend and make a confidence interval that reaches 2 standard deviations, I will definitely encapsulate the true mean. What that means is the only sample means, or the only confidence intervals that won't reach the true mean are those that occur out here, right? Because if my sample mean's out here somewhere, and I extend 2 standard deviations, that won't reach as far as to encapsulate the true mean. And how often does that happen? Only 5% of the time. So the point is, if I get any sample mean within this range, and then I extend 2 standard deviations either side, I will definitely encapsulate the true mean. I will have caught it in my trap, so to speak, and that happens 95% of the time. Only 5% of the time do I go and form a confidence interval like this, and the true mean is not anywhere in that. I'm glad that doesn't happen very often. Let's go with another example. We can look at the average number of hours playing video games per week. Some of you do that a lot, some of you don't do it very much, but we can still look at the average. This time when we go with something, I don't know the true mean, which is what happens in real life. But I go take a sample, and let's say my sample mean happens to be 17, and my sample size happens to be 36. Something we're going to have to deal with in this chapter is not knowing the true mean, which we never know in real life. but we're going to have to go with the assumption that we do somehow know the standard deviation, one thing at a time. So this chapter, we're not going to know the real mean, but we will pretend that we know the standard deviation. We will move on to see what happens in real life when they don't know the standard deviation, but again, one thing at a time. So let's say the standard deviation of the population is 12. There's a pretty wild variance in terms of number of hours of playing video games. But if I want to know the standard deviation of the sampling distribution, I can, like we normally do, take and divide the standard deviation of the population, divide it by this sample size, square root of the sample size, and I get a smaller number. And it reminds us that sampling distributions are much less variable than the populations themselves. So just like I would have done over here, I take my sample mean, because it's the only thing I have to base things on. That's the best information I have. And I'm going to go up and down 2 standard deviations just like I did over here. Because we know that if I do that, 95% of the time, I'm going to catch the true mean in my trap, so to speak. This is the standard deviation of the sampling distribution, and we all know that 2 times 0.5 is 1. So this corresponds to 17 plus or minus 1. So my confidence interval then extends from 16 up to 18. So that just happens to be a span of 2. And we say I am 95% confident that the true mean, which I don't know, is somewhere between 16 and 18. Now again, be careful. That does not mean that the true mean is between 16 and 18. You can't say that, because I might have gotten one of these bad samples way out on the edges, on the fringes, and I don't know that. You can't say the true mean is probably between 16 and 18. It either is or it isn't. Just because we don't know the answer does not allow you to attach any probability to it. All you can say is, and this is a stock statement, so get used to it, I am 95% confident that the true mean is between 16 and 18. Not that it is, not that I hope that it is, not that it's probably. I am 95% confident. And let's not substitute other words like I'm 95% sure, even though in real life that people might use those words interchangeably. We are 95% confident that the true mean is between 16 and 18. What does that mean? They're going to ask you that question too. What that means is 95% of the sample means that I set down and then extend 2 standard deviations either side form a confidence interval which does contain the true mean, and 5% of them just don't do a good job. What if I wanted to be even more confident? What if 95% confidence is not good enough for you? I want to be even more confident. Think of a dart board. I might only be 10% confident that I can hit a bullseye, or even less. I might be 25% confident that I can fit in here. I might be 50% confident that my dart will hit somewhere in there. And maybe I'm 99% confident that I can at least hit the board somewhere. The point is, if you want to be more confident, you have to give yourself an even bigger target. So a 99% confidence interval would have to extend even further. If you want to be more confident, you have to give yourself a bigger target. But the question would be, well, if I want to be 95% confident, I realize from this discussion I only have to go 2 standard deviations either side of the mean, of the sample mean. How far would I have to go if I wanted to be 99% confident? I know it's further than 2 standard deviations, but how far is it? And the answer lies in a picture again of a normal distribution. In the normal distribution in your book, which has a mean of 0, here's the point. If I want to cover 99% of the population, that leaves 0.5% here and 0.5% there. That's what covers 99%. And if you go and look in the front of your book, to get to the 99.5 percentile or the 0.5 percentile, that's how you say that, you have to go up and down 2.58 standard deviations. I suggest you look that up in your book to see how that works. But the idea is if I wanted to form a 99% confidence interval with the same information, the only difference would be I would replace the 2 by a 2.58. Again, if I want to be more confident, I have to make myself even a bigger target. And that's the way that works. So I'd like you to take this, look at this video, obviously. You can run it back if things don't make sense. We're going to do it in class again. You need to see this information probably 3 or 4 times. And then I'm going to send you a relatively short homework assignment, because we have to move on. So please watch this, come in with the questions that I'm going to assign done, and we'll make the best we can of some more snow days. Thanks.